In this video, we'll be looking at how to perform an internal pipe flow analysis in SIMULIA Fluid Dynamics Engineer. This is a follow-on to a previous tutorial we did performing an internal pipe flow analysis in SOLIDWORKS flow simulation. So we'll be making a couple comparisons to this video, and it'll also be linked in the video description below. SIMULIA Fluid Dynamics Engineer is a general-purpose CFD and thermal analysis package on the 3D Experience platform. It features a modern user interface, 16 cores of built-in solve, either local or on the cloud, with the ability to expand that up to 144 cores on the cloud through tokens or credits. Access to multi-physics simulation to couple fluid dynamics results with your structural analysis. The ability to collaborate with other users on the cloud using the simulation collaborator role. Advanced turbulence modeling, like the SST-K omega model, and automated body-fitted mesh, like we see below. The physical capabilities supported are broad and cover a wide range of possible applications. Now, getting into our specific setup and what we'll be covering in this video, we're going to start off from how to get our geometry from SOLIDWORKS into the 3D Experience platform, defining scenarios with our boundary conditions, generating a mesh inside the Fluid Scenario Creation app, solving locally and on the cloud for a second variation, how to interpret our results and generate a report, and also how to take advantage of that ability to view the results on the cloud in your web browser. This video is really intended to be a crash course on how to use this tool, in addition to being an overview of its basic functionalities. So feel free to use the timestamps below if you're just interested in seeing how a certain function works. You can skip ahead. Otherwise, hopefully this can serve as a jumping off point for anyone looking to use the tool. I should also note that this was recorded in 3D Experience R2023X, and as time goes on, you may see slight changes in the user interface for future versions. Finally, if you're doing just a one-off analysis, you can drag something like a step file directly into the Fluid Scenario Creation app, but the workflow I'm going to show here is how to upload your files from SOLIDWORKS, which I think will be relevant for many users of this tool and is a bit cleaner file management wise. Okay, so to get my geometry into the 3D Experience platform, I'm going to open the Design with SOLIDWORKS app, and we'll revisit our pipe assembly that we used previously in another tutorial. As far as preparing this geometry for SIMULIA Fluid Dynamics Engineer, we have a CFD configuration that has some of the unnecessary components suppressed. And this isn't necessarily required, but something additionally I did was insert a new part into the assembly, edit that part in context, and then I used the join feature in SOLIDWORKS, which is kind of a hidden command. So join will allow you to combine multiple different bodies, like all of these different elbows and everything were separate parts, into one body. So that'll just make things a little simpler to manage inside our CFD setup. Also note that we don't need to cap the openings with lids because we'll be able to specify them as openings directly within Fluid Dynamics Engineer. So once we have our geometry kind of prepared the way we want it, we can access our 3D Experience add-in and save this up in there. I like to use the Save As With options so that we can specify bookmarks if we want to. So here under Bookmarks, I can select a bookmark. I'll add a new one and call it Internal Pipe Flow Analysis. Then we can assign that bookmark to our assembly, and it'll just be a tag that we can easily find it with if we want to. Next, I'll save these geometries and they'll be uploaded to the cloud. Now in my Bookmark Editor, which is another one of my pinned favorite apps, I can see all the new items that were uploaded under this bookmark. If you're not seeing them right away after uploading new files, you may want to switch this index or database mode to database mode, which will provide a more instant update. And now to begin the CFD setup, I just need to pre-select the physical product I want to analyze and launch the Fluid Scenario Creation app. Now we can see our products loaded in, and our simulation title we'll set to Internal Pipe Flow Analysis. We'll call this first analysis case our baseline case. We'll reduce the number of maximum iterations to just 750. Click OK. All right, now, as we begin our setup process, you'll see on the left-hand side, I have a feature tree. This can be collapsed, so make sure I would recommend to expand it and pin it so we can see the structure of our CFD setup. And I would also recommend to enable the assistant, which we see on the right. If you accidentally have this closed, then you can get to it under the button right here for assistant. And with this assistant up, we can basically work our way top to the bottom to set up this analysis, starting with the model, where we can choose model setup. The bounding part is correctly identified as our part here. The regions is where we want to select a face on the inside of the model, since this is going to be an internal analysis. And we basically want to see that that little cuboid is on the correct side of where we want the fluid. And then the openings is where we would normally specify things like our lids, or where we have inflow or outflow conditions. So we'll click the little plus sign here, and we'll simply select what's going to be our inlet. This is a 5-inch inlet, so I'll name it as such. And then we'll select what's going to be our first outlet. This is a 4-inch outlet. And then finally our second outlet. This is a 5-inch outlet. So again, we don't need to cap off these openings, we just need to specify them as openings within the model. Finally, we have default settings for our mesh resolution, which we're just going to leave at the default conditions here, and click OK. Now we need to assign the material to the fluid domain. You can see our warning here saying that the fluid section 1 does not have any reference material. If you expand out the properties right here, we can see the fluid section 1. If we double click on it, we can see that we have no material assigned. So we can just click the little search. And I know I'm going to want to use water here, so I'll type water and hit enter or refresh. And I have this previously defined material for water that I'll add in and click OK. Now under physics, we'll check physics behavior, and this is where we're going to define our main analysis case. So it's going to be a fluid problem. We'll also specify a turbulence model, and for these we have advanced models like SST-K omega that can provide high accuracy for external flow problems, and simpler models like the realizable K epsilon that are well suited for internal pipe flow problems like this. And finally, additional settings we could enable, such as the effects of gravity. I'm also going to set the gravity direction to be in the Y direction here, and click OK. Now you can see many of the next items are optional. We're not going to set any initial conditions, but we do need to set boundaries. These are going to be our inflow and outflow conditions. So I'm going to specify a velocity inlet. And what I can do here is under the abstractions, I can see the list of my openings that were already defined. So I'll just select my inlet and set the velocity right here to 3 meters per second. we're going to do a similar thing with the outlets. These are going to be pressure outlets. So I'll choose the 4-inch outlet and click OK, and create another one for the 5-inch outlet and click OK. Zones and loads would be for things like heat sources. We don't really need to worry about any of these other things. Output requests are fields that we want to save out of the simulation and would correspond to goals in SOLIDWORKS flow simulation. When we created those boundaries on the openings, we automatically were creating output requests on these as well. So you can see that there's output requests created on these openings here. So that'll allow us to track things like the flow rate or pressure at any opening. So I don't really need to create any additional output requests. We're at this stage ready to just go and simulate. But if you'd like to generate the mesh manually ahead of time, you can expand the nodes and elements, double-click the hex mesh, and that will yield a pop-up window like you're seeing on the screen here with the default settings for maximum and minimum size, and the number of boundary layers and the first element size. Now, I didn't touch any of these settings. I just clicked mesh, and we've kind of skipped ahead to already take a look at the mesh that was created. To get a closer look at this mesh, I've just hidden our spool solid geometry. And then you can also create section views where if you turn off exact section, you'll be able to see the boundary layer elements inside. You can also just click and drag to section anywhere through the model. If we're happy with this, I'll show my geometry again, and we can move on to solve the analysis. Now, before I do that, you'll want to decide whether you want to solve on the cloud or on your local machine. We'll go to the Simulate tab on the Assistant. For this first analysis, I'm going to solve it on my local machine. So I'm going to go to my results storage and store the results locally as well. I'd recommend keeping that a 1-to-1 ratio, where if you're going to solve on the cloud, store the results on the server. If you're going to solve locally, store the results locally. That way you're not wasting time uploading and downloading the files. So when we're ready, we can go ahead and click Simulate. And we can see that we can solve locally, either interactive or non-interactive, which would be like a background task, or on the cloud. And with the default license of SIMULIA Fluid Dynamics Engineer, you get 16 cores of solving included, which happens to be how many cores I have in my PC. And I'll also choose to generate experience content, which is going to be simulation results that can be viewed within the browser for anyone using the Physics Simulation Review app that we'll take a look at later. So I'll go ahead and click OK. And it basically skips over the mesh generation process since we already did that manually. And I'm going to go to my plots here in anticipation of the solve. So the local interactive is going to allow us to view our progress over multiple iterations. So we can see the different field output requests that I can plot. Now that we're into the solve, we can see my CPU usage going quite high here and my partial results starting to stream in. We can also see solver information on this iterations tab with each increment or iteration and what the error and residuals are. And we're hoping to see these residual values get very low over time. And actually, we set a maximum number of iterations or increments at 750, but the solution will automatically stop if it achieves convergence before then. Okay, so after just 3 or 4 minutes, it looks like we have our results. So we can close our solver monitor here, and we can see an output plot. The default one we're presented with is for pressure. but we can see also things like velocity vectors if we want to visualize that. And we can see for the various different time increments, of course, for steady state analysis like this, we're really only interested in the last time increment, but we could switch to the initial values if we wanted to. Now, additional types of outputs are going to be available in a couple different ways. We can use the assistant to create maybe something like streamlines. And it's nice to just use the automatic method here for the streamlines and click the check mark. And this is basically going to seed some what we would call flow trajectories in SOLIDWORKS flow simulation here to allow us to visualize the flow through the pipes. And we can look at this color-coded in different ways, whether we want to use velocity. When we're done with the streams, we can deactivate them and go back to maybe our pressure plot here. Now the other thing we might want to get out is the history of any key values over our iterations. And so for that, it's actually not on the assistant. It's going to be under our plots right here. And we can choose XY plot from history. And this is going to allow us to capture any of our global values that were measured, like our residuals. Or I can choose something like a pressure or mass flow rate and choose from a particular support. So if I want to take my inlet pressure, then this is what I would do right here. Or I can do all regions, which will show me the inlets and the outlets. And this is going to allow me to visualize the inlet pressure in red and then the two outlet pressures in green there, green and blue. Okay, and we'll also be able to create an automated report, which we'll come back and look at later on, but you'll see many more familiar results types, like we could plot values along a path and so on. Now what I'd like to do is analyze a second case where we'll have just a single outlet. And also we'll solve that one on the cloud. So if we go back to scenario and then our setup tab, you'll see we have various options, like we could do a parametric design study if we want to vary parameters over a table. But if we just want to make a simple duplicate of our analysis, then we can do that over here where it says create a new analysis case, but click the little pull down arrow to duplicate the analysis case. And we'll call this one just single outlet, and we'll use the same settings otherwise. And really what I need to do is, under my flow conditions, I'm just going to disable this second pressure outlet. So actually I'll just delete it here. So now we have still the velocity inlet, but just one pressure outlet. And so for this one, I'm going to solve it on the cloud. And so to do that, under Simulate and my results storage, I'll just make sure that it's set to server. I'll go on down to the Simulate button here and click Simulate. And this time we'll set it to cloud. Now we could use default configuration. I'm going to specify 16 cores, which is the amount of solve that's included with the license. You can use up to 144 cores by consuming additional credits or tokens, but we've got essentially an unrestricted amount of 16 core solve that we can do on the cloud. But we'll use 16 cores and also generate the cloud content again, the experience content. So we'll go ahead and click OK. There will be a slight delay for the cloud solution to begin based on your internet upload speed, since it does need to upload the files to the cloud, and then also the time to provision an instance. So we're just going to skip over that delay here. It was maybe a minute or two. I do think it makes sense to maybe make sure your initial study can run first locally, and then when you want to do more refined runs, longer runs, variations, send those off to the cloud. So after everything's been uploaded and the cloud instance has been provisioned, we can see that we're getting our residuals and everything updating here without tying up and using any of my local computer's resources. So the cloud simulations should be especially useful for very large simulations and solving them quickly with up to 144 cores, or for situations where maybe you have a whole bunch of design iterations that you want to test. Note that we can always close the simulation status window and continue to allow this to solve in the background, and we'll receive a notification on the 3D Experience platform once the analysis is completed. Okay, so our analysis is complete, and this one we can see did take the full 750 iterations. So we'd want to check and make sure that our residuals are quite low, which they seem to be here. But if you were concerned about it, you could always extend the number of iterations and continue to solve this. Just show you what that notification looks like. You can see I received a notification on the platform that the simulation was completed. Now we can close down the solver monitor and interpret our results for the single outlet case. Or I can jump straight to generating a report, which will allow me to compare both configurations. The first time we do access the results for the new case we ran on the cloud, you'll see there's a little icon that those results are on the cloud. So we're just going to download those to our local system to do the post-processing. And we can see updated velocity vectors and streamlines and so on for this case. Now, I'm interested in generating a report to compare the two. So I'll click the report tool and we can choose the types of information we want to include for both cases, as well as add any type of header information we want. And when we click OK, this report will be generated and saved up onto the platform. Here we can see the results of the report, which includes both cases, our major boundary conditions, and our key results outputs. Finally, results can also be compared directly on the platform using the Physics Simulation Review app. This allows comparing different design variations or iterations directly within the browser. So hopefully you found this video helpful as an introduction to performing fluid dynamics analysis on the 3D Experience platform using SIMULIA Fluid Dynamics Engineer. This tool can be valuable for a number of reasons. If you're interested in more advanced turbulence modeling, like the K-omega SST model that's provided, if you want to take advantage of cloud compute with up to 144 cores, or if you need to collaborate with multiple people sharing simulation results through the web browser. As always, hopefully this video was helpful, and let us know in the comments section down below if you have any questions and what type of content you'd like to see next.